For any help regarding solid mechanics assignment help, visit https://solidworksassignmenthelp.com/. Email info@solidworksassignmenthelp.com or call us at +16786484277. Problem 1. A solid aluminum circular shaft has length 0.35 m and diameter 6 mm. How much does one end rotate relative to the other if a torque about the shaft axis of 10 Nm is applied? Problem 2. What if a solid circular shaft is replaced by a square shaft whose diagonal is equal to the diameter of the original circular shaft? How does the torsional stiffness change? For the same torque, how does the maximum shear stress change? What if the solid circular shaft is replaced by a square shaft whose side is equal to the diameter of the original circular shaft? How do these change? Problem 3. A thin aluminum tube, whose wall thickness is 1 mm, carries a torque 80% of the torque required for the onset of yield. The radius of the tube is 20 mm. Show that an estimation of shear stress, based upon the assumption that it is uniformly distributed over the thickness of the tube, and using an estimate of J that is linear in the wall thickness, gives a value within 10% of that computed using the full expressions for shear stress and polar moment of inertia. Solidworksassignmenthelp.com. 1. We turn to the stiffness relationship in order to determine the relative angle of twist, L phi, over the length of the shaft, L for a solid circular shaft, the moment of inertia, J is equal to pi r/2. The shear modulus G is related to the material's elastic modulus and Poisson's ratio by G is equal to, and the elastic mod, Euler's for aluminum, found in the table on page 212 is 70 E09 Nm2. Taking Poisson's ratio as 1/3, G then evaluates to 26 E09 Nm2. Putting all of this together gives L an angle of rotation radians. The maximum shear stress is obtained from this evaluates to max is equal to 2.36 times 10 Nm2. This is the change 12th November 2004. What follows is an excursion which considers the possibility of plastic flow in the shaft. We see that the maximum shear stress is near or greater than 1/2 the yield stress, in tension, of the 3 types of aluminum given in the table in Chapter 7. So what will ensue? Solidworksassignmenthelp.com. To proceed, we need a model for the constitutive behavior that includes the relationship between shear stress and shear strain beyond the elastic range. We assume elastic perfectly plastic behavior, i.e., that shown at the right. Beyond the yield point, no further increase in stress is gamma required to produce an increase in strain 1. Consider the shear stress distribution at some instance beyond the R is equal to RR is equal to R onset of yield. Onset of yield will occur when the shear stress at the outer radius of the shaft, R is equal to R, attains the value tau y. With some additional loading, some additional torque applied, the shear stress distribution over the radius might appear as at the left. We show the material yielding in the region of the cylinder beyond some radius, R is equal to R, where the subscript I denotes the radius at the interface of the elastic and perfectly plastic regions. In that region of plastic flow, the shear stress is everywhere equal to the shear stress at yield, tau y dot at R is equal to R. The shear stress and strain are just tau y and gamma y respectively. The material within the core of the shaft, RE, continues to deform elastically. Solidworksassignmenthelp.com. Within this elastic region, we have a linear distribution of both stress and strain with R, which can be written. This stress distribution results in a torque, which we obtain from an integration over the area of the entire cross-section. We have where we have taken account of the rotationally symmetry of the problem, carrying out the integration with respect to theta, giving the factor to pi. Carrying out the integration with respect to R yields this relationship, which holds only after some outer portion of the shaft has gone plastic, shows how the torque, metric ton, increases as re decreases as more and more of the shaft enters the plastic zone. The onset of plastic flow happens when re is equal to R. We label the torque when this happens mild. Solidworks assignment help.com. Likewise, we can define the angle of twist at the onset of yield. We have now past the point of the onset of plastic flow at the outermost radius, when the shear stress distribution appears as shown in the figure above, at R is equal to re R, we have these two expressions for gamma y enable us to write we can now eliminate the yield shear stress from R express for the torque beyond onset of yield, replacing it with the torque required at the onset of yield, and also eliminate the radius to the interface, replacing it with the angle of twist at the onset of yield. We have for phi is equal to yield. While for phi is equal to yield, we have linear elastic behavior. At the interface, Solidworks assignment help.com. We plot and see, from the above expression for metric ton, letting it very large, that the shaft can sustain a torque of up to 4/3 the torque for onset of yield. Of course, the angle of twist increases without limit as we approach this ultimate torque. 2. The figure at the right shows the first case. Here the length of side of the inscribed square, which we call to are expressed in terms of the diameter of the circle is. The torsional stiffness of the solid circular shaft is pi r 4/2. That for the square shaft is obtained from the textbook, page 232. There we find metric ton is equal to kt file where kt is equal to gk1, to am, 3 to b. In terms of the radius of the circle, putting a and b in terms of the radius r gives. Solidworks assignment help.com. A table gives the value for K1 for the case when 2A is equal to 2B as 0.1406. So we obtain KT is equal to 0.36 GJ, where J is the polar moment of inertia of the solid circular cylinder. The inscribed square shaft has a torsional stiffness of 36% of the solid circular shaft. The maximum shear stress is obtained from a second relationship found on page 232, and now we have. This factor is 1.0 for the circular shaft. The maximum shear stress in the inscribed square shaft is 2.67 times greater than the maximum shear stress in the solid circular shaft. For the square shaft circumscribing the cylinder, we have A is equal to R. We find in this case that the square shaft is stiffer in torsion than the circular shaft by a factor of 1.43. And the maximum shear stress in the square shaft is just a bit smaller than the maximum shear stress in the circular shaft, a factor of 0.94. Solidworks assignment help.com. 3. For a hollow shaft, the polar moment of inertia J is given by where ρ and re are the outer and inner radii of the shaft. Thus, the approximate shear stress is within 10%. Solidworks assignment help.com.